in the previous lecture we investigated the characteristics of a small current element, what is called the Hertz dipole. We saw that Hertz dipole is not a very efficient radiator because the radiation resistance is very small. So, if you have a dipole of length 0.1 lambda, it gives you a radiation resistance of only about 8 ohms. So, in practice the Hertz dipole does not have much utility. However, the Hertz dipole has now created a foundation for investigating more complex antenna structure. So, the logical next step from the Hertz dipole is to investigate the radiation characteristic of a linear thin dipole. That means, if I consider now a piece of wire which is having a length comparable to the wavelength, then what would be its radiation characteristic? That means, what will be the radiation pattern, what will be the input impedance of this antenna, what kind of polarization will be created by this antenna. These are the issues. If we investigate, then this antenna can be used in practice. So, dipole antenna is one of the antennas which finds a wide application in the field. In fact, some time back most of the TV antennas were essentially the dipole antennas. So, as the name suggests, this is a dipole, that means there are two halves of this antenna and its antenna is excited at the center. So, essentially the structure is a linear wire which is excited at the center either by a voltage source or a current source, and let us say the length of this wire is 2h, that means half of this dipole is h. So, we have this is h, half length, and this is h. And you can excite this at the center. Because of the excitation at this point, the current now is going to spread out on these wires, and as we have seen, as the extreme case of flared up transmission line, the dipole antenna can be visualized. So, without going into much detail of how the current distribution is obtained on the dipole, we will essentially investigate the radiation characteristics assuming that the current distribution on the dipole is known. As I mentioned earlier, the current distribution calculation is a rather complex issue. In fact, you require methods like method of moments or other numerical techniques to find out the current distribution on this wire in a self consistent manner. However, if once the current distribution is given to you, then finding the radiation pattern and input impedance, that is very straightforward thing. So, in this course we do not investigate how the current is calculated on the dipole. We assume by some crude arguments the variation on the dipole, and when the variation is known, the current variation is known, then we can visualize this dipole as collection of small Hertz dipoles, and then simply by applying superposition we can find out the total electric field due to this dipole. So, as we had put forward the argument that if you consider a transmission line which is open circuited at this end, then you have a reflection at this end of the transmission line. So, the current is 0 at this point, and you have a standing wave which will be created on the transmission line. Similarly, this will happen on the other wire of the transmission line. So, if the current is flowing here this way, the current will be flowing in the opposite direction on the second wire. Now, if you slowly flare up, so that ultimately it becomes a completely opened up version which is the dipole, then this thing can be visualized as a flared up version of this transmission line, and the current distribution still, if we say, is this. Where this current here will be flowing upwards, this current also flows upwards. So, essentially the current which is going to be here, they will be in the same direction. So, here the current flows like that, here the current flows like that. So, the current will be coming out of this, the current will be going inside this. So, you can think of this as connected by a voltage or current source to the input terminals of the antenna. Now, the rigorous calculation also show, as I mentioned, the rigorous method like method of moments or some other methods, that if the dipole is very thin, then the current essentially flows along the length of the dipole, and then in an ideal case, when the diameter of the dipole is practically 0, then the current distribution on this dipole is almost sinusoidal. So, we know the distribution, and that we can see from the flaring up of the transmission line also, that if this is a standing wave, then we have a sinusoidal distribution on this, which is a standing wave pattern. This pattern remains even when the antenna is completely flared up to become a dipole. Now, of course, at this point it is not very convincing that when the transmission line is completely flared up, still the arguments like standing wave patterns and all are valid, but it so happens that even the rigorous solution gives you the same kind of current distribution as you would have got from the standing wave pattern on a transmission line. So, essentially now we know the current distribution, and few logical tests we can conduct on the current distribution, and that is, when we go to the tip of the antenna, the current must go to 0 because now there is no path for the antenna, and that is also true in case of transmission line, that if you have an open circuited transmission line, the current at the open circuited end must go to 0. Also, we know that on the transmission line the current is symmetric. So, two conductors have equal in opposite direction for the current. However, when you have a flared up version of this, the currents travel in the same direction. So, you have a symmetry of the current distribution on the dipole, and you have the current 0 at the tip of the dipole. So, essentially these are the two conditions under which one can investigate the problem. That means the input current which flows on the antenna is not in the control of the designer. What he can do is he can simply design the length of this antenna, since the current has to go to 0 at the end of the antenna, and this function is a sinusoidal function. Depending upon the length, it might have a certain value of the current at the input terminal of the antenna. So, input terminal current is decided by the length of the antenna. There is no independent control of controlling the current for a given voltage excitation. Once we have this current distribution, then we can visualize the dipole antenna as a collection of the Hertz dipoles. So, let us say first I define the coordinate system. So, as we had done earlier, this is let us say y direction, this is the x direction, this is the z direction. So, I am assuming that the dipole antenna is oriented along the z direction, and it is having a current which is I of z, which will be given by the standing wave pattern which we have got on the transmission line. Now, as we said, this dipole can be visualized as the collection of small Hertz dipole. So, let us say we divide this into small pieces, and at a height of z from the center of the dipole, we have a small infinitesimally small current element, let us say that is dz, and the current which flows in this dipole is given by Iz. So, we have here current which is as a function of z, and then there is a small current element we are considering at a distance z from the origin along the dipole dz. So, the field at a very far away point, because now we are considering only the radiation fields. So, essentially we should go to a distance substantially far away from the dipole, so that the electrostatic and induction fields have reduced to a very small value. So, essentially we have got only radiation field. That means we go very far away from the antenna. Theoretically we should going to infinite distance from this, so that the other two fields go to 0, and then we apply the superposition of the fields due to each of these small current elements. So, let us say I measure all the distances from the center of this dipole, and let us say I want to measure a field which is at a very far away point in the direction which makes an angle theta with respect to the z axis. So, these two are to a far away point. So, since the point is very far away, these two lines are almost parallel. So, if I drop a perpendicular from this point on this line, then the field which is generated from this current element will be travelling a distance shorter compared to the reference point, which is the center of the antenna. Or in other words, the field which are induced because of this, the radiation fields at far away point, that will be leading in phase corresponding to a distance which is this distance. So, if this angle is theta, this angle is also theta. So, this distance which you have here is equal to z cos of theta. So, we have got here a distance, this one, which is z cos of theta, because this angle is also theta. So, what that means is that the radiation coming from this dipole, Hertz dipole, with respect to the center of the antenna leads in phase corresponding to a distance which is z of cos theta. So, while superposing the field, we have to put an additional phase which is corresponding to this distance. Now, the current distribution which you have on the antenna is come from the standing wave pattern. So, this thing can be written as I of z, that is equal to some maximum value I m sine of beta h minus mod of z. You can verify this is mod of z. So, when z is equal to 0, you have a current which is I m sine of beta h. However, when z is equal to plus minus h, that time the current will go to 0. So, we will have a current distribution which will be something like that. So, the current distribution for the dipole, if I write on separate figure, it will be like that, where this is the value which is I of m, and the height of this antenna is 2h, that means half of the antenna height is h. So, this is the current distribution which we have, that is essentially given by this. So, I know now the current distribution on the dipole, and which I write down explicitly for z less than 0, which is lower half of the dipole, and z greater than 0, which is for upper half of the dipole. I can explicitly write the current which is I of z is equal to I m sine of beta h minus z for z greater than 0 and equal to I m sine beta h plus z for z less than 0. So, this thing which you have written, the current distribution, now explicitly we can write this for the lower half of the dipole, which is for z less than 0, and for upper half of the dipole, which is for z greater than 0. Once we know this current distribution, as we said, we simply apply the find out the field because of the infinitesimally small current element, find out the extra phase which is coming because of the distance, and simply superimpose the field over all antenna elements. So, we will get total field at a far away point, which will be the electric field due to the entire dipole. So, let us say now the Hertz dipole which we have got, that is this Hertz dipole, and now we are treating this like an incremental element. So, the electric field which is generated by this current element, let us call that as E theta. We know that the Hertz dipole which is oriented in z direction generates an electric field which has only theta component. So, since all these elements are oriented in z direction, all the elements are going to generate only theta oriented components. So, if I go to a very far away point, the electric field due to all of these elements are going to be in the same direction. So, essentially we require only a algebraic addition of the electric fields, because they all are oriented in same direction, theta direction, and apply with the proper application of the phase which is coming because of the extra length introduced by the path. So, the infinitesimally small current element, the Hertz dipole fields, is be derived. Let us call that now E theta, d E theta, that will be equal to j beta square sin theta divided by 4 pi omega epsilon I of z into dz, that is now the current element, because at location z the current flowing is Iz, this is the length of the current element. So, this is the current moment for that infinitesimally small element divided by r1, that is the distance of the point from this. So, let us say this is r1 and distance from the center is given by r. So, here this will be r1 e to the power minus j beta r1, and as we know, the wave radiation field essentially generates a transverse electromagnetic wave. So, the magnetic field is related to the electric field through the intrinsic impedance of the medium. So, the magnetic field d h phi will be nothing but d E theta divided by the intrinsic impedance of the medium. So, we do not explicitly calculate the magnetic field for the dipole, we simply calculate only the electric field, and as we know this relation, as and when the magnetic field has to be calculated, we can divide the electric field by the intrinsic impedance of the medium and we can get the magnetic field. So, we essentially do most of the discussions only for the electric field whenever we discuss the radiation characteristics of an antenna. Now, as I mentioned, the r1 is a distance which is shorter compared to r by this distance. So, I have r1, that is r minus z cos theta. I can substitute now for r1 because I am measuring all the distances from the center of the dipole. So, this quantity will be e to the power minus j beta r minus z cos theta, and this will be again r minus z cos theta. Now, what we do, if you look at these two quantities here, one is this one which is coming in the denominator, here the r is coming in absolute term. What it means is that the electric field now is going to change equivalent to replacing this r1 by r. If I do that, then there will be correction which will be coming due to this quantity. Now, since we are considering a distance which is very far from the antenna, the maximum z we can have on this antenna which is equal to h, this h is much smaller compared to r. That is what we have in practice for radiation field. So, we have for radiation field r is much greater than h, and since z is always going to be less than or equal to h, this quantity the r is much greater than h. Typical example is, let us say if I take a dipole antenna which is having a size of let us say lambda or lambda by 2, let us say if I am operating at a frequency of 100 megahertz, the wavelength will be 3 meters. So, the dipole size will be of the order of about 1.5 meter, 2 meter, 3 meter, something like that. However, when I use this dipole antenna for sending radiation, I will be sending radiation over distances of few tens of kilometers. So, R will be of the order of kilometers, whereas H will be of the order of only few meters. So, this condition R is much greater than H is very well justified when we go in the calculation of the radiation field. So, this quantity R1 can be replaced by R, because this quantity is much smaller than this quantity in this term. Can we do the same thing here? Can we replace R1 by R in this expression also? The answer is no, we cannot do that. The reason is that here we are talking about now the change in distance, but now this is related to lambda, because when you multiply this quantity by beta, this is going to be beta z cos theta, which is a phase, and this phase, absolute phase does not have any meaning. When you talk about a phase change comparable to pi, you have got essentially the cancellation of the two fields. So, here when we talk about the approximation, here the distances absolutely do not come into picture, they are relative distances, because this is the phase quantity, and when the phase becomes comparable to pi, you cannot really neglect the effect of the phase change. However, in this case the amplitude does not get significantly affected, because this R is much greater than H. So, we can make, with this understanding, we can now make an approximation to this field d theta, which is approximately j beta square sin theta upon 4 pi omega epsilon I of z dz upon R. I am replacing R1 by R in this, and this will be e to the power minus j beta R minus z cos theta. So, now all these quantities are not function of z except this phase term and this current distribution now. Then, as we said, now the total field which we are going to get here is superposition of these fields. The phase term is now accounted for, which is this z cos theta. So, the total field which we are going to get due to this dipole now will be integral of this d theta over the total dipole length. So, we get now the total radiation field E theta, that is equal to j beta square sin theta upon 4 pi omega epsilon r e to the power minus j beta r integral minus h to h I of z e to the power j beta z cos theta to dz. So, I have simply substituted for the d theta and integrated over the total length of the dipole, which is from minus h to h. So, from here I just find out now the integral from minus h to plus h, and I get the total electric field from the dipole. We can substitute now for the current of the two halves, as we have got here, for z less than 0 and z greater than 0 separately, and can find out the total integral. If we do that, then this quantity can be written as j 60 Im. There are all constants which are there, they have gone into that, like beta will be related to the frequency and the permittivity and permeability of the medium. So, this will be Im e to the power minus j beta r upon r and will be some function of theta, which we can write explicitly. The reason for doing this is the amplitude term which you are going to get at a distance of r, but as we saw, we are interested in essentially relative distribution of the field as a function of angle, what we call as radiation pattern. So, this function of theta essentially will be the radiation pattern for this dipole, that is what we are interested. How do you get these parameters here? We know this quantity beta is omega square root mu epsilon. So, we can take this term here beta square upon 4 pi omega epsilon. So, this term will be, so beta square upon 4 pi omega epsilon will be equal to omega square mu epsilon divided by 4 pi omega into epsilon, which is equal to omega mu upon 4 pi, or we can write this as beta eta for the intrinsic impedance of the medium also upon 4 pi, and when we integrate this we are going to get 1 beta which will cancel with this beta. So, essentially you will get this quantity eta, divide this which is 125 for the free space impedance. So, this will be equal to 30 beta. So, having this quantity beta square upon 4 pi omega epsilon equal to 30 beta, if I substitute here, then this integral essentially will get simplified to this. So, as I mentioned, this term essentially gives you now a variation of amplitude of the electric field as a function of r, and that we have seen for the Hertz dipole, which varies as 1 over the distance. In this case also the same thing is true, that the electric field amplitude will be inversely proportional to a distance from the center of the dipole. We also have a phase term which is e to the power minus j beta r, which is same as what we get for a spherical wave which has travelled a distance r from the source. So, this term we are not worried about. If we are interested in finding out the absolute amplitude for the electric field, then we can make use of this. However, we are more interested in this quantity, what is called the radiation pattern, and this one, when we solve this integral, so we get what is called radiation pattern, and as we have mentioned, the radiation pattern is a normalized quantity. So, this total constant does not really matter, we want only relative variation of the field amplitude as a function of angle. So, radiation pattern would be f of theta equal to cos of beta h cos theta minus cos of beta h divided by sin theta. Just if you solve this integral, that is the thing essentially we are going to get as a function of theta. So, now we get a radiation pattern for the Hertz dipole, and then we can also calculate what is the input current when the length of the Hertz dipole is given to you. So, the two quantities in which you are interested in, one is what is the relative distribution of the electric field as a function of angle, other one was for a given length of the dipole how much is the input current for a given excitation of voltage. So, without losing generality, if I say that excitation is 1 volt at the terminal of the dipole, then the current whatever is there in the terminal, 1 upon that current will give me the input impedance of the dipole. So, we get input impedance of the dipole, which is Zn, which will be 1 upon the current at the input of the dipole, that is at z equal to 0. So, if I substitute z equal to 0 in this, I m sine of beta h, that will be the current. So, I m sine of beta h. So, one few things can be noted now immediately, that the input impedance, which in some sense has to be a measure of power radiated by the antenna, is no more a monotonic function of the length of the antenna. We saw that in the Hertz dipole, the radiation resistance was related to the length of the dipole in the square fashion, that the radiation resistance was proportional to square of the length of the dipole. However, in this case the input impedance is having a rather complex relation. So, it depends upon the value of h. So, you have a sinusoidal distribution on the dipole, and then depending upon the value of h, you may get some value of the input current. So, the input impedance may vary over a very wide range. In fact, when this quantity is pi by 2, that time the input impedance will be 1 upon I m, whereas when this quantity is 0 or pi, that time this will be 0 and the input impedance will go to infinity. So, because current will go to 0. So, I may get the highest value of the input impedance, which will be as high as infinity, and I may get the lowest value when this is maximum, that is 1. So, that will be equal to 1 upon I m. So, essentially the input impedance now may vary from 1 upon I m to infinity, and when this quantity is 0 or pi, when that will happen? When beta h is equal to pi, but beta h is equal to 2 pi by lambda into h. So, when beta h becomes pi, that will be when h is equal to lambda by 2. So, the lambda will cancel, 2 will cancel, we will get pi. So, the total length of the antenna will be 2h, which will be equal to lambda. So, if I consider a dipole of 1 wavelength long, then its input impedance will be infinity, because in that case the current will go to 0 at the terminal. If I consider now h lambda by 4, then this beta h will be pi by 2, and I will get the minimum input impedance of the antenna. So, this value essentially corresponds to h equal to lambda by 4, and this value corresponds to h is equal to lambda by 2. Of course, these are not the unique values. This quantity will go to 0 again for 2 pi and multiples of that. So, as the length of the antenna increases, you will see that the impedance will become 1 upon I m, again it will go to infinity, again it will come to 1 upon I m, and so on. So, there is no monotonic trend for the variation of the input impedance as the length of the dipole changes. What happens with the radiation pattern when we change the length of the antenna? That is also very complicated. Again, immediately it is clear that as the length of the antenna increases, this function might have multiple maximas, and this function might go 0 too many times as a function of angle theta. So, normally instead of investigating the radiation pattern in great detail, what we normally do very roughly, we try to see what are the directions in which the radiation pattern becomes 0. That means, what are the directions in which there is no electric field. If you take two consecutive directions where the electric field has gone 0, then in between these two directions the electric field must have gone to maximum somewhere. So, the calculation of the maximum electric field or direction of maximum electric field is rather a tedious task, but finding the direction where the electric field goes to 0, that is rather simpler, because we can equate this radiation pattern to 0 and we can find out the directions for which the electric field will go to 0, and then we say roughly between two consecutive directions of 0 field, there must be a direction where the electric field goes to maximum. These directions where electric field goes to 0 is what is called the directions of nulls. So, null is in radiation pattern is defined as that direction in which the electric field is 0. So, we can get now the directions for nulls by equating the radiation pattern of this dipole to 0. So, I can get this by cos of beta h cos theta minus cos of beta h upon sin theta, that is equal to 0. Or from here I have cos of beta h cos theta will be equal to cos of beta h, or beta h cos theta will be equal to plus minus beta h plus minus 2 m pi, where m is an integer. So, m is equal to 0, 1, 2 and so on. From here then I can find out the directions of the nulls. So, cos of this angle null, that will be equal to plus minus 1 plus minus 2 m pi upon beta h, and beta is 2 pi by lambda into h. So, that is equal to 2 pi will cancel. So, this will be plus minus 1 plus minus m lambda by h. So, we will have nulls whenever this condition is satisfied. So, knowing the value of h, I can try for all possible values of m for which the cos theta magnitude is less than or equal to 1, and that will give me the directions for the nulls. So, first thing we notice is as the h increases, there will be more values of m, more and more values of m, for which you will have this quantity less than or equal to 1. That means there will be multiple directions in which the electric field will be 0. So, the number of nulls will increase as the length of the dipole increases. One thing however can be verified, and that is when m is equal to 0, cos theta is equal to plus minus 1, that means theta corresponds to the direction theta equal to 0 or theta equal to pi. So, there is the null which is in the direction theta equal to 0 and theta equal to pi. However, one should notice that when theta is 0 or pi, even this quantity goes to 0, the denominator goes to 0. So, just blindly we cannot say that at theta equal to 0 there is a null, because we have to actually find out what is the limit of this expression when theta goes to 0 or pi. And one can verify that when theta goes to 0, in fact the limit of this expression goes to 0. So, there is indeed a null in the direction of theta equal to 0 and theta equal to pi, and that makes physical sense also, that since the dipole is a collection of the Hertz dipole, and Hertz dipole has a null along its axis, that means that theta equal to 0 and theta equal to pi, the superposition of the field also should be 0 in that direction. So, since the individual element which is the Hertz dipole, in which we divided this dipole into, has null in the direction of theta equal to 0 and theta equal to pi, every linear dipole also has a null along its axis. So, if I go along its axis either theta equal to 0 or theta equal to pi, a dipole will have a null in that direction. That means the dipole does not radiate along its length, along its axis. it always radiates in the direction which is not along the axis. Does it always radiate perpendicular to it, as was the case in Hertz dipole? That is not that straightforward. In fact, as we said, we find out the directions of the nulls, and approximately we say between two nulls there will be one maximum. So that we have to see for different lengths of the dipoles what would be the radiation patterns, and from there we can broadly try to visualize the radiation patterns. So we can take some specific cases and find out the radiation patterns of the dipoles. So let us say if I take a length of the antenna which is lambda by 4, this quantity now h is lambda by 4, so dipole length is lambda by 2. This quantity will be, so let us consider length, take some case 1, where h is equal to lambda by 4, that means the dipole is lambda by 2 long. So cos of theta for the nulls will be equal to plus minus 1 plus minus m lambda upon lambda by 4. So that will be equal to plus minus 1 plus minus 4m. Any value of m which is not equal to 0 will make this quantity greater than 1. So that means there are nulls only corresponding to m equal to 0, and these nulls are the same at theta equal to 0 and theta equal to pi. So if you are having a dipole of length lambda by 4, then you get the only same nulls which are theta equal to 0 and theta equal to pi. So the dipole now is of lambda by 2 length. So this length is lambda by 2, and there are only two nulls, one in this direction, other one is this direction. The pattern is symmetric in the phi direction because the Hertz dipole also has a symmetric pattern in phi direction. So superposition again will give me the pattern in phi direction which is symmetric. So these two nulls are there, and since the problem is symmetric, there has to be a maximum between these two nulls. So the maximum is in this direction. So we get a radiation pattern which is same as the Hertz dipole radiation pattern for an antenna which is this. So this radiation pattern is identical, at least shape wise, to the Hertz dipole. So by changing a length of the antenna from Hertz dipole to a physically realizable length which is lambda by 2, the radiation pattern does not get significantly altered. The nulls remain same, the direction of maximum remains same. So this is the direction in which we have maximum radiation. Now note here there is no one direction, here the entire plane is the direction in which the radiation is going maximum. So as we had seen yesterday, this is the figure of, this is like an apple. So if you take the cut of the apple vertically, that is this radiation pattern. We can increase the length of the antenna and go to case 2, that is I increase the length of the dipole, h is equal to lambda by 2. That means I have made now dipole which is one wavelength long. So in this case now cos of theta will be plus minus 1 plus minus lambda upon lambda by 2. So will be plus minus 1 plus minus 2. Again it should be m here. Again for m equal to 0 we have plus minus 1 nulls, but for m equal to 1 also, those nulls for which this value will be, magnitude will be less than 1, again would correspond to only plus minus 1. So the directions of nulls are still theta equal to 0, theta equal to pi. So even for a dipole which is one wavelength long, which is this is now lambda. The directions of nulls are still the same, which is theta equal to 0 and theta equal to pi, and the direction of maximum again because of symmetry will be halfway. So, direction still remains same, which is maximum like this. So, the radiation pattern becomes something like that. Again there is a direction of maximum. So, till we increase the length of the dipole up to lambda, the shape of the radiation pattern does not change significantly. Of course, something must be happening. So, if I say this apple gets more and more compressed like this, so this thing becomes little elongated, it does not remain like a simple sin theta function. So, this radiation now, this variation as a function of theta become little more sharper compared to this, but qualitatively the radiation pattern still has two nulls and it has direction of maximum, which is like this. Shape still resembles very much like an apple, though it is a compressed apple. However, once I go beyond this, take one more lambda by 2. So, if I take now case 3 where the h is equal to 3 lambda by 4, and in this case we will get cos of theta equal to plus minus 1 plus minus m lambda divided by 3 lambda by 4, that is equal to plus minus 1 plus minus 4 upon 3 into m. And now one can see that you can get now the nulls for m equal to 1 also by appropriate sign. So, by taking appropriate sign for m equal to 1, we can actually find out the nulls corresponding to 1 also, which will be for which this quantity will be less than 1, the magnitude of this will be less than 1. So, those angles would exist. So, I can get a radiation pattern for this dipole. So, there will be now nulls corresponding to m equal to 0, which will be theta equal to 0 and theta equal to 1, and there will be nulls corresponding to m equal to 1 also. So, now we got nulls theta which will be equal to 0 pi, and if I take m equal to 1, I would take the sign appropriately. So, this will be, if I take plus 1 sign here, I have to take minus 4 by 3. So, this becomes minus 1 by 3. So, that will be corresponding to cos inverse of plus minus 1 by 3. So, now the length of the dipole has become 3 lambda by 2, and the directions of nulls are now, one is this theta equal to 0, theta equal to pi, but I have got two nulls which are symmetric, one is in this direction, other one is this direction. And as we said, between every two nulls there has to be maximum radiation. So, now the radiation pattern would look something like that. And it is the figure of revolution. So, essentially you will get a pattern which will look something like that. So, we got now directions for nulls. Earlier there were only two directions. Now, in fact, you got a cone like this over which there will be nulls, and there will be maxima now which are multiple, because there is a radiation which is maximum here in this, there will be maximum here, and so on. And as we saw earlier, the radiation pattern is a 3-dimensional figure. So, essentially what we are seeing this as a section of a 3-dimensional figure. So, if the 3-dimensional figure, if I imagine by revolving this around the axis of the dipole, the radiation pattern would essentially look like that. So, this corresponds to h is equal to 3 lambda by 4. So, you see here this is the direction of null which we have shown. This is another direction of null. So, all these directions there is no radiation in this. There is a direction here which is maximum. There is a direction null here again, which is here, and there is a null which is going downwards. So, this looks more like some kind of a flower vase which is created. So, the radiation in 3 dimension essentially would look like a flower vase for a 3 lambda by 4 length. So, our understanding that as the edge increases there will be more nulls, radiation pattern will become more complicated. That is what essentially appears from here. We can take one more case, and that is, let us say, case 4, where H is equal to lambda, and then the cos theta will be equal to plus minus 1 plus minus m lambda by 2 lambda. So, that will be equal to H is equal to lambda. So, there is no 2 lambda here. So, that will be equal to plus minus 1 plus minus m. Again, what we will notice that m equal to 0 will give me the tape 2 nulls, but m equal to 1 also gives me the null, which will be again same as plus minus 1 with the appropriate sign. So, now when the dipole length has become 2 lambda, I again get only 2 nulls which are in this direction, but now there is one null which will be coming here corresponding to when this quantity goes to 0, that means theta becomes equal to pi by 2. So, I got one more null in this direction which is null. So, I got 3 nulls, and the radiation pattern now would become something like this. So, if I revolve this around the figure, around the axis of the dipole, we will get a radiation pattern which is like this. So, this is for H is equal to lambda. So, now we draw a very important conclusion that as the length of the dipole is increased, the radiation pattern gets modified, more nulls come, but there is no systematic evolution of the radiation pattern, and the impedance which you see for different lengths of the dipole also does not change systematically as the length of the dipole. We will investigate more characteristics of the dipole and in general other antennas from the radiation patterns.